Good afternoon. This podcast is going to focus on looking at atomic level defects, both point and line defects, their effect on the physical properties and mechanical properties of the material, as well as look at the brassing of a penny lab and what happened in that lab. I'm Miss Mikesell, and I'm one of the materials science teachers, and I hope this podcast is helpful. I would encourage you to get out a piece of paper and a pencil, pause me, and take notes as we talk through this. At the atomic level, a defect is when a piece of metal is made up of a large number of crystal grains where there's regions of regularity, and the grain boundaries of the atoms have become misaligned. So we can see in this picture to the right, we have some extremely regular atomic packing occurring, and yet right here at this region, we have a defect or a area where the grain boundaries, the atoms have become misaligned. So again, if we look at the second image below, we can see these regions of extreme regularity, and then we can see these defects or areas right along the boundary of a grain where atoms are not in their correct position and are misaligned. Defects, though, in crystals are actually a good thing because imperfections allow for ductility, the ability of the metal to be stretched into a wire, and malleability, the ability of the metal to be flattened and formed into useful shapes. So natural crystals are almost never perfect. All have some defects in their crystal structure. Today, we're going to start by examining point defects. Point defects are a defect or irregularity within a crystal that occurs at a point in the crystal lattice, which can influence the crystal's properties, including its color. There are three types of point defects. The first one is called a vacancy defect. In a vacancy defect, atoms are missing from the lattice structure. So we can look and see a vacancy defect that we should expect an atom to be right here, and it's missing. So there's a gap in the crystal lattice structure, or that region of regularity where we'd expect an atom to be. And we can clearly see defects in our atomic model over here to the right that are vacancies, areas where we'd expect an atom to be, and those atoms are not present. A substitution defect is when different atoms have taken the place of existing atoms within the crystal structure. So we can see on our image below that we have our bulk atoms, or most of the atoms in this crystal structure are blue and represent one type of atom. And then we have this substitution, this orange atom that's taken the place. And finally, the third type of point defect is an interstitial defect. That's when extra atoms are stuck where they don't belong. Generally, these extra atoms are much smaller than the bulk atoms, and they fit into some of the empty spaces. So this is an interstitial alloy, and we can see the bulk atoms are the green atoms, and our extra atoms, which are stuck in places they don't belong in the crystal lattice, are the purple atoms in the picture. So here's another way to see all three of those defects in one material. An interstitial defect, again, is an atom that's stuck in a place where it doesn't belong. In this case, in this model, our interstitial defect is an atom that is the same as the bulk atoms. It's just stuck in a place where it doesn't belong. Whereas a substitution defect can be an atom that is smaller compared to the bulk atoms, and it has been substituted in the crystal lattice in a place where an atom should be. Or in this case, it is a larger atom than the bulk atoms, but again, it's been substituted in place of an existing atom within the crystal structure. And then a vacancy defect is when atoms are missing where they should be in the normal lattice structure. So if we look, defects are one of the reasons why gemstones can be different colors. Both sapphires Blue sapphires, green sapphires, and red rubies are all made of aluminum oxide. And if we look at the structure of aluminum oxide, we can see the oxide ions right here, the larger oxygen, as well as the aluminum right here, which are the black molecules or atoms in this picture. And generally, aluminum oxide is clear and colorless if it's pure aluminum oxide. But blue sapphires result from substitutions of titanium within the crystal lattice, as well as iron atoms. Green sapphires result from iron impurities being substituted into the crystal lattice, and chromium being substituted in forms red rubies. So when we have defects or substitutions within the crystal lattice of something besides aluminum and oxygen atoms, we get a different color gemstone. So let's just do a quick check. Right now, what type of point defect do you see? Is this a vacancy, substitution, or interstitial defect? Hopefully you said this one was substitutional. Agreed. What about this image? You should have chosen interstitial. And finally, this one's pretty obvious. Hopefully you said it was a vacancy defect. All right, let's look at line defects. Line defects are lines in which whole rows of atoms in a solid are in irregular positions. This is also known as a dislocation. If we recall what we were looking at a few classes ago, when we stretch our bonds significantly, we're going to have elastic deformation. And if those bonds are stretched until they break, that would be plastic deformation. Obviously, line defects have a significant effect on the mechanical properties of the material. So we can see the line defect right here in the picture because this is where an entire row of atoms is missing and it's not in its regular position within the crystal lattice. And we can see if there is a force applied, that line defect can move and slide along the crystal lattice until eventually it reaches the edge. And this is known as an edge dislocation. Let's show an animated visual of that. So that line defect is being moved along until it reaches the edge of the crystal lattice, and that becomes an edge dislocation. So an edge dislocation is when a plane of atoms is inserted into a plane in the crystal structure. We're going to watch a quick video about this because it's an excellent example that walks through an edge dislocation and its effect on some mechanical properties.
The purpose of this screencast is to discuss the concept of dislocation and plastic deformation. So let's say that you have a bowl of cold ice cream and a spoon. So if you go ahead and take a bite out of the ice cream and you put your spoon in the ice cream and it bends, but it does not go back to its original shape, what you have just experienced or what you have just observed at the macroscopic level is a large number of dislocations moving. Another way that we end up describing this is plastic deformation. So let's go ahead and take a look at what a dislocation is. So if we have a metal that is solidifying, we're going to expect that during solidification, it will actually end up forming for us a lattice. So sometimes the lattice that ends up forming has a defect in it. And these defects are what we call dislocations. So if our defect is a situation where we end up having part of the plane not forming, we end up calling this an edge dislocation. And you can see how our lattice has a missing atom. So in yellow is where our missing atom is. This becomes a problem if we end up having a situation like our spoon with our ice cream. So if we go ahead and we place a force on the side, and this would be similar to if we went ahead and dug that spoon deep into that ice cream, what we'll end up finding is that our bonds along plane 2, so right along this plane, they start to stretch on us. and then they'll eventually break. And once they end up breaking, we end up having a situation where right at this point, you will find that these bonds are going to actually end up breaking and reforming and allowing us then to have plane number one will end up having a full plane. The result is that your defect in your material in your lattice is now moved. It's no longer along plane one, but instead it's along plane two. If we keep applying our shear force, what's going to end up happening is our dislocation is going to keep moving. So our defect will keep moving all the way to the end. So then we're going to have a situation where our final lattice will end up looking like this. In this case, our edge dislocation has moved all the way to the end, so now it's in plane 4. One of the things that's really good to remember, though, is that what you're seeing here is a single dislocation moving. This was all we had in this example. However, anytime we see plastic deformation of a metal, we are seeing several dislocations, large numbers moving all at once. So a little bit different than the example that we have here. So the definition of slip is plastic deformation through or produced rather by dislocation motion. Another concept that's associated with dislocations is this idea of dislocation density. So as our materials end up solidifying, we end up having different types of dislocation densities associated with that metal. So dislocation density is defined as total dislocation length per unit volume. What you'll end up finding is different type of processing that we do actually will increase our dislocation density. For instance, processes that can increase your dislocation density would include cold rolling. Another process that may end up increasing your dislocation density would be cold forging. In these cases, we're assuming that our material is above its recrystallization temperature. We're assuming that our material is below its recrystallization temperature. So for cold rolling and for cold forging, these are examples of processes below recrystallization. So just remember, the next time you end up permanently deforming a metal, what you have actually done is a large amount of dislocation motion.
So what happens when a force is applied to an edge dislocation? And the answer to that is it causes the bonds to break. And so once the bonds break, we become plastically deformed. That means that we can't return to our original shape of the material. So defects, both point and line, change the mechanical properties of a material or how a material responds to force or stress. And if we look at properties that can be determined by mechanical stress, we'll be measuring things like tensile strength, compression, hardness, fatigue. In other words, the lifespan of the material or how long it can stay intact over time, as well as things like impact and torsion. So let's look at an example of a tensile test or a way to test a mechanical property of a material.
Wouldn't that be damaging? I don't know. We have the advertising on safety cord, you know? Yeah,
hopefully you can start to see some necking or an area where that metal is being elastically deformed. Ooh, and we had a brittle fracture. So how do dislocations affect malleability and ductility? And how do dislocations impact work hardening and affect hardness and brittleness? Dislocations increase malleability and ductility because there's empty space for the atoms to move to. So the more dislocations that are present, the more malleable and ductile your material will be. How do dislocations impact work hardening and affect hardness and brittleness? The more dislocations there are in a metal, the easier it is for the dislocation to tangle if they're cold worked below the temperature. And that would increase both hardness and brittleness. That's that example we saw in the video regarding ice cream. So when we look at how you change the properties of a metal, as a material scientist, we have 4 approaches. We can make it from different stuff. Think about our material selection. We can add different stuff to it. In other words, create an alloy. We can heat treat it and cool it at different rates, quench or anneal it. This will change how many defects are present in the material, how the atoms are aligned within the crystal lattice. Or we can disrupt the crystal structure by work hardening or cold foraging something. So the BB case activity we did in class looked at that example of quenching or annealing, changing the rate at which we cool a substance. Let's watch a quick video to show you what you should have seen in that activity.
At the atomic level, as the body pin is heated, the metal atoms move more freely, and during the gradual cooling, the atoms slow down and settle back into a very orderly array with few defects.
So when our material was cooled gradually, we can see that the atoms have plenty of time to find their proper positions within the structure, and there's less defects present.
At the atomic
Let's compare that to if we abruptly cool our substance.
At the atomic level, as the metal is heated, the atoms move more freely, but the abrupt cooling process leaves many defects in the crystal structure.
So the faster we cool our material, the atoms have less time to get into their locations within the crystal lattice, and we get more defects. That will change the mechanical properties of the material. So let's take a second and look at the brassing a penny lab we did. We started with our original copper-plated penny. We then plated it in zinc before eventually turning it into a brass penny in the lab. If we consider our original penny, if we cut a penny in half, we know that it is made of mostly zinc with a small, thin layer of copper around the penny. If we were going to draw an atomic view picture of that, we would be drawing a picture that shows mostly zinc atoms in the middle with a thin layer of copper atoms around the surface of the penny. When we put the penny into our hydroxide solution that had zinc inside of it and used electricity to plate it, we essentially added another layer of zinc, another very thin layer of zinc around the outside of the penny, coating it in zinc. So just like the original zinc was coated in a thin layer of copper, now we've added just one more layer to the penny, and it is zinc colored on the outside because we've created another thin layer of zinc around the outside of the penny. But then we put it on a hot plate and we heated it up. And when we took it off the hot plate and put it in water and quenched it, we ended up with this brass penny. What would that look like on the atomic level? Why did we add it to the hot plate? How did the atoms in this shift as we put it on the hot plate? Hopefully you drew an atomic model that showed the copper and the zinc atoms now moving and changing positions and being mixed together within the penny. If we think about what happens, brass is a homogeneous mixture and it's a substitutional alloy. The copper and zinc atoms are substituting and taking each other's respective places within the crystal lattice. The heat from the hot plate causes atoms to gain energy. They become mobile enough to diffuse and mix and become part of each other's crystal structure. This is known as solid-state diffusion. It occurs due to vacancies in the crystal structure. We need those vacancy defects because two atoms cannot exist in the same space. So for diffusion to occur, there must be some empty spaces. This is akin to one of those slot games you play as a child where you're trying to move and organize your pieces to match whatever image was that was rolled. And so there have to be vacancies, empty spaces, so that the copper and zinc atoms, when heated, are mobile enough to move and fill in those spaces and to mix together. And finally, if we looked at one of the ways that we could change the properties, that was through work hardening. And so if we consider what happens in work hardening, we have an edge dislocation. And as we look at this line defect, it is being moved along the crystal lattice until it reaches the edge. And then that edge dislocation creates a pinning. The atoms have nowhere else to go, and so they are pinned or stuck. And this pinning is creating the hardened effect because the atoms are now stuck into position and tangled. So the metal is now work hardened or significantly harder than it was when it was over here. If you have a pure piece of metal, you can control the size of the grains by heat treating or working the metal. Banging the metal around when it's cold tends to create the tangle dislocations, increasing the hardness and brittleness. And in order to get it back to being workable, you would need to reheat it so that the atoms could move in their crystal structure back, removing the pinning and work hardening process. So one last thing that we want to summarize. How would each type of vacancy that we studied affect the thermal conductivity? And remember that thermal conductivity is the ability of electrons to carry energy in the form of heat. And so what we're really looking at is how mobile the electrons can be through the material. Electrons in the metal move around. They are conducting heat more easily than they can through ionic solids or covalent network solids. So if we consider our three types of defects, vacancy, interstitial, and substitutional, which one of those would have the largest effect on thermal conductivity? Hopefully you told me vacancy would, because a vacancy defect provides irregular spacing, so that's going to have the biggest change, the biggest decrease in conductivity. Whereas interstitial, those impurities affect the regular atomic spacing and thus the flow of electrons, but it will have a smaller impact on the thermal conductivity than a vacancy defect would. Whereas substitutional has the smallest decrease in thermal conductivity because it has the lowest effect on spacing and thus the mobility and the flow of electrons.